Good morning. In this part of the course, we introduce the transmission parameters of two-port networks. These parameters are also known as ABCD parameters or chain parameters. They are particularly useful when two-port networks are connected in cascade because the overall transmission matrix is obtained directly by matrix multiplication. We will first review the two-port representation, then define the transmission parameters, study cascade connections, derive the parameters of several useful circuits, and finally establish conversions between impedance and transmission parameters. This part is organized into 6 sections. We begin with a brief review of the two-port network. We then define the transmission parameters and examine the important property of cascade connections. Next, we derive the transmission parameters of several useful two-port circuits, including basic series and shunt sections, transmission lines, transformers, and common T and pi networks. Finally, we develop the conversion from impedance parameters to transmission parameters and the inverse conversion from transmission parameters back to impedance parameters. Before introducing transmission parameters, let's recall the concept of a two-port network. A two-port network is a circuit or network with two pairs of terminals, called ports. Each port is characterized by voltage and current. The first port is described by V1 and I1, while the second port is described by V2 and I2. Different parameter sets can be used to relate these 4 variables. The transmission parameters provide one particularly convenient representation, especially for cascaded networks. Here we exactly define the voltage and current variables associated with the two ports. At port 1, the voltage V1 is measured with the indicated polarity, and the current I1 is directed into the network. At port 2, the voltage V2 has the indicated polarity, while the reference direction of I2 is also known. These reference directions are important. In the transmission parameter formulation, the second port variables are arranged according to a chosen sign convention. We must therefore maintain the same convention consistency throughout the analysis. We now introduce the transmission parameters. The transmission representation relates the variables at one port to those at the other port. Depending on the convention adopted, 2 equivalent forms are commonly introduced: the A parameters and the B parameters. These are called chain parameters because they describe how the variables are transferred from one port to the other. The advantage of this representation becomes especially clear when two-port networks are connected in cascade. For the A parameters, the output variables are related to the input variables through a 2x2 matrix. The 4 coefficients are defined using open circuit and short circuit conditions at port 2. Specifically, A11 and A21 are obtained with I2 equal to 0, corresponding to an open circuit at port 2. The other 2 parameters are obtained with V2 equal to 0, corresponding to a short circuit. The B parameters use the reverse relationship. The variables at port 2 are expressed in terms of the variables at port 1. In this case, the defining conditions are applied at port 1. We now consider one of the most important applications of transmission parameters, the cascade connection of two-port networks. Suppose 2 networks are connected in cascade. The output port of the first network is connected directly to the input port of the second. The intermediate variables are V2 and I2. The transmission representation allows us to express the variables at the first port in terms of these intermediate variables, and then the intermediate variables in terms of the variables of the final port. This leads naturally to a simple matrix multiplication rule for the complete cascaded network. For the two-port network, the vector containing V1 and I1 is obtained by multiplying its transmission matrix by the vector containing V2 and I2. Similarly, for the second network, V2 and I2 are related to V3 and I3 through the second transmission matrix. Substituting the second relation into the first gives the K result. The transmission matrix of the cascaded network is simply the product of the individual transmission matrices. Therefore, if the 2 networks have matrices T1 and T2, the overall matrix is T equal to T1 multiplied by T2. This simple multiplication property is the main reason transmission parameters are so useful for analyzing cascaded two-port networks. We can extend the cascade principle to any number of two-port networks. For three networks connected in cascade, the overall transmission matrix is obtained by multiplying the three individual matrices in their physical order. Thus, the matrix of the complete network is the product of the first, second, and third transmission matrices. This result generalizes immediately to an arbitrary number of cascaded two-port networks. The cascade property gives transmission parameters a major practical advantage. When several two-port networks are connected in cascade, we do not need to analyze the complete circuit again from the beginning. We simply determine the ABCD matrix of each individual section and multiply the matrices. This is particularly useful for communication systems, filters, matching networks, and transmission line sections, where complex systems are often built from simpler cascaded blocks. Let's now determine the transmission parameters of some basic two-port networks. We begin with the series impedance Z. Using the transmission equations, the voltage at port 1 is related to the voltage at port 2 by the voltage drop across Z, while the current is unchanged through the series element. Comparing these relations with the ABCD definition gives A equal to 1, B equal to Z, C equal to 0, and D equal to 1. Next, consider a shunt admittance Y. The voltage is the same at both ports, while the input current differs from the output current by the current through the shunt admittance. Applying the ABCD definition gives A equal to 1, B equal to 0, C equal to Y, and D equal to 1. The corresponding matrix is therefore lower triangular. In this example, we determine the transmission or ABCD matrix of a section of lossy transmission line. The line is characterized by three physical parameters: its complex propagation constant gamma, which includes both attenuation and phase propagation, its characteristic impedance Z0, and its physical length L. Our objective is to establish the matrix relation between the voltage and current variables at the two ports. We use the standard transmission parameter convention in which the current at port 2 is represented as minus I2. This sign convention is particularly convenient when networks are cascaded. Before proceeding with the derivation, it is useful to recall that transmission line theory applies to many physical structures, including coaxial lines, parallel wire lines, waveguides, and planar lines such as microstrip. Although their geometries and field distributions are different, the transmission line model provides a common framework for describing voltage and current waves. In the present example, the specific geometry is not important. What matters is that the line is characterized by its propagation constant and characteristic impedance. We now consider the actual two-port model of the lossy line. At the input or port 1, the voltage and current are V1 and I1. At the output or port 2, they are V2 and I2. The line has characteristic impedance Z0, propagation constant gamma, and length L. The voltage and current can be represented as the superposition of forward traveling wave and a reflected or backward traveling wave. The coordinate Z is measured along the line from Z equals 0 at port 1 to Z equals L at port 2. For a lossy transmission line, the propagation constant is gamma equals alpha plus j beta. The parameter alpha describes attenuation, while beta describes phase variation along the line. The voltage and current are written as the sum and difference, respectively, of the forward and backward traveling waves with the exponential factors accounting for propagation and attenuation. At Z equals 0, the line variables are simply V1 and I1. At Z equals L, the voltage is V2 and the current is minus I2, according to the transmission parameter convention. These boundary conditions allow us to express the wave amplitudes in terms of the output variables. Applying the boundary conditions at Z equals L gives two simultaneous equations involving the forward and backward wave amplitudes. We then solve these equations for V0 plus and V0 minus. The resulting expressions contain exponential factors involving gamma L and the combinations V2 minus Z0 I2 and V2 plus Z0 I2. This step is important because it allows us to eliminate the unknown wave amplitudes. We can now substitute them into the expressions for the voltage and current at port 1, obtaining the desired relationship directly in terms of the port variables. Substituting the wave amplitudes into the input voltage and current equations, we obtain expressions for V1 and I1 in terms of V2 and I2. Using the identities for hyperbolic functions, the exponential terms combine naturally into hyperbolic cosine and hyperbolic sine functions. We therefore obtain V1 as V2 hyperbolic cosine of gamma L plus Z0 I2 hyperbolic sine of gamma L. Similarly, I1 is V2 over Z0 multiplied by hyperbolic sine of gamma L plus I2 hyperbolic cosine of gamma L. Comparing these equations with the standard transmission matrix definition immediately reveals the four ABCD parameters. We can now identify the transmission matrix of the lossy transmission line section. The A and D parameters are both equals to a hyperbolic cosine of gamma L. The B parameter is Z0 hyperbolic sine of gamma L. And the C parameter is 1 over Z0 multiplied by hyperbolic sine of gamma L. This is the general ABCD matrix for a uniform lossy transmission line. As an important special case, consider a lossless line for which alpha equals 0 and gamma equals j beta. Using the identities for hyperbolic functions with an imaginary argument, the matrix reduces to the familiar trigonometric form involving cosine and g sine. Thus, the lossless transmission line matrix is obtained directly as a special case of the more general lossy line result. In this example, we determine the transmission or ABCD parameters of a two-port network consisting of an ideal transformer. The transformer is characterized by its turns ratio defined as n equals n1 divided by n2, where n1 and n2 are the numbers of turns on the primary and secondary windings, respectively. Our objective is to determine the transmission matrix whose four elements are the parameters A, B, C, and D. The key point is that for an ideal transformer, the voltage and current relationships are known directly from the turns ratio. We will use these relationships to identify the four ABCD parameters. We begin with the fundamental relationships of an ideal transformer. The voltage ratio is equal to the turns ratio. Therefore, V1 divided by V2 is equal to N1 divided by N2, which is simply N. We can therefore write V1 equals N times V2. The current ratio follows the inverse relationship. The current at port 1 is equal to the current at port 2 divided by N. These two equations completely characterize the ideal transformer from the viewpoints of the two-port network model. Notice that the voltage is multiplied by N while the current is divided by N. Consequently, the ideal transformer transfers power without loss, subject to the chosen port current conversion. We now compare the transformer equations with the standard definition of the transmission parameters. The first transmission equation expresses V1 in terms of V2 and minus I2. Since V1 equals N times V2 and contains no term involving I2, we immediately identify A as N and B as 0. Similarly, the second equation gives I1 as 1 over N times I2. With the transmission convention, this leads to C equal to 0 and D equal to 1 over N. Therefore, the transmission matrix of the ideal transformer is diagonal. Its diagonal elements are N and 1 over N, while both of diagonal elements vanish. Let's summarize the result. For an ideal transformer with turns ratio N equal to N1 divided by N2, The transmission matrix is a diagonal matrix with elements n and 1 over n. The parameter A represents the voltage transformation ratio, while D represents the corresponding inverse current transformation ratio. The parameters B and C are 0, indicating that there is no direct dependence of V1 on I2 or of I1 on V2 in the ideal transformer model. Finally, the determinant of the transmission matrix is equal to AD minus BC, which gives 1. This confirms that the ideal transformer is a reciprocal two-port network. The final slide shows the circuit representation of the ideal transformer with the turns ratio indicated as n to 1. The primary winding corresponds to port 1, while the secondary winding corresponds to port 2. Under the ideal transformer assumptions, there are no losses, no leakage effects, and no parasitic elements included in the model. The corresponding transmission matrix is therefore simply the diagonal matrix containing n and 1 over n. This example illustrates an important advantage of transmission parameters. Once the individual ABCD matrix of a basic two-port element is known, it can be readily combined with other networks, particularly in cascade configurations. The ideal transformer can therefore be treated as a simple building block in the analysis and design of more complex microwave networks. Let's now derive the transmission matrix of a two-port pi network. The network can be viewed as a cascade of 3 elementary sections: a shunt admittance Y1 at the input, a series impedance Z3, and a shunt admittance Y2 at the output. Since we already know the ABCD matrix of each elementary section, the total transmission matrix is obtained simply by multiplying these 3 matrices in their physical order. We begin by multiplying the matrices corresponding to the input shunt admittance and the series impedance. This gives an intermediate matrix whose upper right element is Z3 and whose lower right element is 1 plus Y1 Z3. We then multiply this result by the matrix of the output shunt admittance. The 4 elements of the complete transmission matrix follow directly from the second multiplication. The resulting ABCD matrix can now be written in terms of the 3 admittances by introducing Y3 equal to 1 plus over Z3. The 4 transmission parameters are therefore expressed entirely in terms of Y1, Y2, and Y3. As a useful check, we calculate the determinant of the matrix. We obtain AD minus BC equal to 1. Therefore, the pi network is reciprocal as expected, since it is composed of reciprocal elements. This slide presents the final transmission matrix of the pi network together with its circuit representation. The compact matrix form is useful as a reference result. It shows directly how each of the 3 admittances contributes to the 4 ABCD parameters. This expression will also be useful when comparing the pi network with its dual T network configuration. We now turn to example 6, the transmission matrix of a 2-port T network. The T network is also a cascade of 3 elementary sections: a series impedance Z1 at the input, a shunt admittance Y3, and a series impedance Z2 at the output. Therefore, as with the pi network, the overall ABCD matrix is obtained by multiplying the 3 elementary transmission matrices in sequence. We first multiply the matrices of the input series impedance and the shunt admittance. The resulting intermediate matrix has 1 plus Z1 Y3 in the upper left position, Z1 in the upper right position, Y3 in the lower left position, and 1 in the lower right position. We then multiply this matrix by the transmission matrix of the output series impedance Z2. This gives the complete ABCD matrix of the T network. To express the result in terms of the 3 impedances, we use the relation Y3 equal to 1 over Z3. The resulting transmission parameters are therefore written in terms of Z1, Z2, and Z3. Again, we can verify reciprocity by evaluating the determinant of the transmission matrix. The result is AD minus BC equal to 1. Thus, the T network is also reciprocal. This slide summarizes the final transmission matrix of the T network together with its circuit representation. Notice the duality between the T and pi configurations. For the T network, the series arms are described by impedances, while the central shunt branch is represented by the reciprocal of Z3. The final matrix provides a compact expression that can be used directly in subsequent network analysis. We conclude this section with the summary of the transmission parameters of the common two-port circuit studied in this part. The elementary series impedance and shunt admittance provide the basic building blocks. The lossy and lossless transmission lines and ideal transformer have their own standard ABCD matrices. More complex T and pi networks are obtained by cascading these elementary sections and multiplying their transmission matrices. The key idea to retain is that transmission parameters are especially powerful for cascaded networks. Once the matrix of each individual section is known, the matrix of the complete network follows directly from matrix multiplication. We now consider the conversion from impedance parameters to transmission ABCD parameters. Unlike the impedance-admittance conversion, this transformation is obtained directly from the defining equations of the transmission matrix. Our objective is to derive the transmission matrix of a two-port network from its impedance parameters. We shall combine the impedance equations with the formal definition of the transmission parameters. We first write the impedance equations and recall the definition of the transmission parameters. Instead of determining all four parameters at once, we calculate them column by column. First A and C with I2 equal to 0, then B and D with V2 equal to 0. Step 1. With the output port open circuited so that I2 equals 0, the impedance equations simplify considerably. Applying the transmission parameter definitions gives the first column of the transmission matrix, namely A and C. Step 2. Next, we set V2 equal to 0. Using the simplified equations together with the transmission parameter definitions yields the remaining elements B and D, completing the derivation. Collecting the four expressions gives the complete conversion formula. Finally, we note that symmetry leads to A equals D, while reciprocity implies that the determinant of the transmission matrix is equal to 1. Consider now transmission to impedance parameter conversion. Derive the impedance matrix Z from the transmission ABCD matrix and compare the two parameter definitions and obtain the conversion formulas. Our objective is to determine the impedance matrix from a known transmission matrix. The derivation follows directly from the definitions of both parameter sets and applies to any linear two-port network. Conversion strategy. Begin with the transmission equations and compare them with the impedance equations. Determine the impedance matrix in two steps. Step 1. Set I2 equals to 0 to obtain Z11 and Z21. Step 2. Set I1 equals to 0 to obtain Z12 and Z22. Step 1. First column. Set I2 equals 0, which means port 2 open circuited. The transmission equations simplify, allowing V1 and I1 to be written in terms of V2. Applying the impedance definitions gives Z11 equals A over C and Z21 equals 1 over C. Step 2. Second column. Set I1 equals 0, which means port 1 open circuited. Solve for V2 over I2 and substitute into the first transmission equation. This yields Z22 equals D over C and Z12 equals AD minus BC over C equals to determinant of T over C. Final conversion formula. Combining both columns gives the complete conversion formula for Z. For a symmetric network, A equals D. For a reciprocal network, determinant of T equals 1, implying Z12 equals Z21.